Hi all, this is Krishna here. I'm working as application engineer at Decibels Lab Private Limited. So, I will be mostly taking care of algorithms development on the batteries, such as like SOC, SOH, SOE, and like BMS functionalities. So, and also working on the implementation at the hardware level. So this is a basic like introduction of mine. So yeah, about today's topic is about like EKF-based SOC and cell temperature estimation. Okay, so I'll just quickly go through this day one and day two agenda, and then like one more small poll is there. So yeah, so
I
in the
just
day one,
I just Krishna, sorry to interrupt. I'll just share the result of the poll.
okay,
Yeah, Krishna, I have shared the results.
okay, um, I think I can continue, right? Yes,
Yeah,
okay, yes. So about the day one, like we'll try to go through the introduction of the Kalman filter and some understanding of it. So like where we can use it and like how it can be used, like in terms of application, like, okay, yeah. And we'll try to understand the mathematical steps involved in the Kalman filter application and the briefly discussion on the Kalman filter family. So when we talk about like Kalman filter, so the day one will be only with respect to the in the general format, because when I talk about like Kalman filter, like we will be using uh, to many systems, like for many applications. Okay, so I'll be talking for day one in the general, like understanding only about the Kalman filter and the mathematics involved in it, and then we can go for the day two, that is cell related, and the like the topic of cell thermal model and the topic related to cell SOC estimation and cell development. Okay, so as I mentioned in the day two, that ECM model in the state space, that we can look into it and whatever the equations involved in it. Okay, and then like for the temperature estimation of the cell, like we are going to bring some thermal model. So for our case, we will be using some lumped analysis approach. Okay, so combining both these models, and we are going to bring like a whole set of state equations. Okay, yeah, and finally, like a small demo of MATLAB program, like I'm going to show you. So which is built like use whatever the results like we are going to see at the end. So we got from the same like program that we can look through a MATLAB program. Okay, yeah. So yeah, in the next, I'll just yeah. So Vinayak, you can run the like last poll, and I'll get into the topic.
okay.
Yeah. So just let us know, guys. Like apart from this agenda of day one, like if you want to explore something, you can just mention in the chat box, so that like if the topics which you mention, if it is not covered in today, so that I can like I can have some time for tomorrow and I can bring some slides related to it. Yeah. So the poll is running. So yeah, it is something related to like some technical aspects. You can just answer, and we'll have like 2 minutes for this poll. So whatever you know, you can just answer it. Yeah. Yeah. So on the thermal runaway, like we can like take it on some other day. We'll arrange a meeting when we talk about like only on the cells and thermal point of view. Uh, we can like bring that webinar. Okay. Yeah. So yes, I think we can end the poll and we can publish the results. Vinayak.
Yeah.
Yeah. Yes. Uh, Vinayak, I'll just continue. Okay. Okay. Yes. So, like as a like many people like don't have much of experience in terms of like knowing the Kalman filters. Okay. So I'll just try to give some the intuitive explanation of it. Like okay, and then we will go into the mathematical equations. Yes. So here the Kalman filters, like they are nothing but the prediction algorithms. Okay. So it is an iterative process of your mathematical process. Okay. Like it has some set of equations and the set of data. So with that, if you give even with any value, it will quickly take to its like true value, giving as a update value. Okay. Yeah. So like if I want to take some example here for the understanding. So like this is some kind of measurement you can take some radar or something, camera or something. So it will just measure the position of your vehicle. Yeah. So I'm just taking example like of a vehicle here. Okay. So my objective is to like get to know the position of the vehicle. So your acceleration will be something like input to the vehicle. Okay. Yeah. So the results will be like velocity and the displacement of this vehicle. So displacement nothing but it tells the position. So here like as we like see this represents assuming that this is your like position at k. Okay. And in the next time step, like let's say like in the next second, your position value will be updated. So how you can say like it is updated because the vehicle is moving with some velocity. So let's say like it is moving with some 100 km per hour. Okay. So presently right now like assuming it is at some position like as I said k, and as it moving in the next second the position can be updated as k plus 1. So I'm just trying to bring a vehicle over here, an imaginary vehicle. Yeah. So in my Kalman filter, like we predict with the help of your theoretical model. Okay. So like you might be thinking like what could be the theoretical model? So theoretical model is nothing but you are representing a car, a behavior. So behavior is nothing but the dynamics of it, right? So you're representing a car model in a mathematics format, and we can call it as theoretical model. So whatever we get estimated, or like the data from that model, we can call it as estimate. Okay. Yeah. So here, like you see, like whatever the data we get from the like from this model. So we put as a acceleration as an input, the value, and the output we get as a position and velocity. Okay. So this is one part of like estimating your values such as like position and velocity. So we can call it as like theoretical model. On the other hand, we are getting the measurement. So when I say the measurement, it is completely from your sensor. Okay. So as I mentioned, I'm using some kind of like camera or like maybe radar or something. So with that, I can measure the position of your vehicle and like velocity, like yeah, all the parameters like I can measure. So that is one more like approach of measuring the vehicle within the Kalman filter. Okay. So yeah. So taking the information from your predict. So while I say predict, it is the data coming from your theoretical model. Okay. Taking the information from the predict and taking the information from your measurement data. So already mentioned that measurement data is nothing but is from the sensors. Okay. And you are updating your the value. Okay. Yeah. So let's say like you are taking the information such as like velocity and the position from your predict. Okay. And the measure from the measurement data also like velocity and the uh, positions from through the sensors. So yeah. So you are going to predict, oh sorry, update the values. Okay. So why we have to like consider why this Kalman filter is having this approach, that is predict and like update or like considering of the measurements. Okay. So we will discuss that point here. So when I say that through measurement model, I am saying that the vehicle position is something like, okay, I'll just randomly put position value. So yeah. So right now the vehicle position is something like 10 meter. Okay. I'm just randomly putting the value. Okay. And now it is 20 meter. Okay. So after like 1 second, it has moved to 20 meters something. Okay. Yep. I'm just assuming this data. So this data, like I'm getting it from my sensor. So you could have said that like why only we can dependent on the sensor, because we already have the sensors and we're getting the positions of the vehicle. Okay. And the velocity is also measurement we have doing. Like why there is a requirement of the state equations, why we have to do the prediction. Okay. So the question is that when you have the data from your sensors, there is something we can say that we can't completely depend on the sensor data. Okay. So because of external factors, there will be some errors, or you can say like noises will be there. So because of those factors, your value, whatever we get, it is not 100% correct. Okay. So assuming like this is something imaginary or like ideal position of your vehicle. Okay. So let's say the actual vehicle could be at like 22 meter. Okay. So this we get it from your predict. Like when there is no influence of anything, and if you measure like through your theoretical model, if you don't have any influence of your external factor, like all considering like a dynamic condition in ideal way, and you measure and you get the data, okay, that is position of your vehicle, and somehow it comes over here, okay, and whatever the measured from your sensor, it is something like at over here, that is at the 20 meter. So even the theoretical, like you cannot say that it's 100% correct because we have not included much of external factors. So even from the measurement, we have the data we got, like it might have experienced the external factors, and also it might have some consisting the noises because of affected by the external factors. So considering all that, like you will be again taking the information of this predict and taking the information of this measurement, and you are going to update. So in the update, there is a term called like Kalman gain. Like once we move to the mathematics part, you will get to know. So that Kalman gain, like it will keep on changing its value, like for every time step. So it will decide that to which uh, set of information I'm getting, like for the information I'm getting from predict and the information I'm getting from measurement, to which I have to give the more weightage. So based on that, it will update the position and the velocity value. Okay. So assuming that I may get over here. So I'll just try to use the different color. So you'll get to know. Yeah. Right. So, so this is the way like you can like if you are like using some normal methods or approaches in terms of doing some estimations, not only for the vehicle in terms of, as we are going to talk tomorrow, that is about the SOC, SOH, all the stuff. So like, yeah, so we can use the Kalman filter to get the more accuracy. Okay. Yeah, I'm not saying that it will be the 100% correct data, but in terms of comparison, it can give the more accurate. So like considering all your noises, sensors, errors, all the stuff. Yep. So this is about like understanding of the just an overview understanding of Kalman filter where it can be used. Okay. Yeah. So next I will go to the steps in the Kalman filter. So yeah, there is a like I can define this in 3 steps. So here also I mentioned that is like one with the initial, I can say it as a step, and in the predict and the update. I'll just write, okay, predict and update. Yep. So in the predict, where it contains your like a theoretical model. So people say something like a digital twin, right? Digital twin. So which will be comes in a use of your AI and ML applications. But like before, like I know like it will work more on the data, but before that, like they start with the mathematical approach itself, representing your a system. Okay. Yeah. So, like whatever the model, like as I was saying, the vehicle model, uh, about if I take the cell, so the cell model, okay, and the battery when it is connected in series and parallel. So all these can be represented in the state equation, which comes in the predict. And we know that when we estimate the data through the predict step, like we get some error, and we call this error as error in estimate. So even that is going to be updated, like the predicted. Okay, yeah. So basically, like predict, and in the measurement, like as I said, a concept of like Kalman gain we are going to see. So and then updating your data. Yes. So there is one more thing. I think it's missing over here. I'll just show you in the next slide. Yes. So here you can see that there is a measurement. So which you are going to get it from sensor. Okay. Yeah. So these are like steps you can see, like the predict, update, and the measurement. With this, like I will try to look into each step, like what all equation is involved. Okay. So the set of equation which I'm showing over here under the blue color line. So these are like a predict to predict the system, and where you are going to initialize your like your state equations. Okay. Yeah. So when you represent a system in a state space, which you already like familiar with this equation, like which you learned in your engineering, like through the control systems or etc. So this is the equation, the state equation, and this is about like the covariance, process covariance matrix. Okay. Yeah. So first, like we'll try to see about this part. When I say that xk, so instead of like the hyphen, I'm going to make it as like k plus 1. Yes, equal to a x k. You can keep it as k or like k minus 1. So if you are keeping as k minus 1, this will become k. Okay. Yeah. So yeah, I'm not like going to the feature, right? I'll just make it k minus 1, and I'll make this as k plus b into u. So this w, you can say it as like a noise. So right now, like for to understand here, like I'll just neglect this part. Okay. Yeah. So this particular, that is x of k minus 1, it will be having like other matrix. Okay. So the rows into column, right? So the rows will be having all your parameters. So if I'm trying to like put a matrix for a vehicle, right? So a basic, a vehicle means like I'll be considering only two parameters, right? One with the velocity, one with the distance. Okay. So this A will be representing your uh, your update equation. Okay. So the B will be having the equation of your, let's say, like if the equation for to like estimate. Okay, so I'll just try to bring it somewhere over here. I'll just try to put it over here. Okay, this is A, this is X of K minus 1 plus B, and this will be your like input. So in our case, like input is your acceleration. Okay, yeah. So B into U. So once like whatever the K, whatever the parameters which are in X of K minus 1, so that represents at that particular time. Okay, means like of the previous time. So when once you multiply with a matrix A and you added with like B and U, so whatever the X update you get, right? So that is with respect to the at that particular time. So this will be of like previous estimate, and this will be of like present estimate. Okay. So with this, you can see that this X of K matrix, like the data you are going to get from your previous state, right? So for example, like if you are doing it for the first time of estimation and you don't have any previous states, then you have to initialize it. So only one time the initialize has to be done. Okay. So when you're doing it for first time, the initial steps will become as a previous step. So once you initialize the data, so whatever the data you put over here, like they are going to go here and you are going to estimate. Okay, you are going to predict the estimate, and you have like you're going to initiate your like uh, a noise, like the covariance matrix. Sorry, so that also is going to be updated. Okay, like you can put over here, and you are going to get the new covariance matrix. So from this, like X, it will be having some set of state data, state variables. Those are nothing but your velocity and the position. So those are going to come over here along with your like uh, process noise. Okay. On the other end, you are going to measure from the sensor. So basically, if I take as a vehicle, so the same thing like the position and the velocity of your vehicle, and that you are going to put it to the Kalman gain equation. Okay. So this R is nothing but a sensor noise, and this P of K, like and the F1 over on the top, like that you can call it as like process covariance matrix, and H is nothing but your observatory matrix. So right now, like we can consider it as an identity and we can neglect it. Yeah. So with these values, based on my noise and the covariance matrix, I'm going to get a gain value. So with this gain value, okay, I can like say that this much of weightage has to be given to the measurement, and some amount of measure weightage has to be given to the like my predict step. Okay, so with this, if you are seeing over here, once you have a Kalman gain, you are going to multiply the Kalman gain with respect to your measurement data. So that is, we're getting it from the measurement. Okay. And this predicted state, so you are getting it from predict step. So I'm just trying to put over here. So I'll just take one variable, that is position. So from the predict step, I got the position value of 22. From the measurement, I got the position value of like 20. Okay. I'm going to take the difference. So I'm getting the error of 2. To this 2, for this value, I'm going to multiply my gain. Okay. So gain is always defined between 0 to 1. So yeah. So once you multiply this gain, and you are going to again add with the predicted step. So whatever the output you are going to get, that is your update value. So this update value will act as a previous value for the second round of estimation. Okay. Or you can take it as a output value. Yeah. So this is like the overview of your like on the Kalman filter. So here, like as I mentioned, yeah, here as I mentioned about, let me bring mention about this noises, right? And the sensor noise. Okay. So your position, like of your vehicle, when you're getting it from the sensor. So it is always depends on your like, uh, means if you want to say like how accurate your sensor. So based on that, you are going to define your R values. Okay. When you are saying like the process noise uh, from your like predict step, when you're defining those, so it is always like based on how well like the dynamics of your system has been included in your state. Okay. When you are like represented your vehicle, when you are represented your cell model, right? So in a state space, so how well the dynamics has been covered through the mathematical format. So based on that, like you have to provide. So when I look for like, there are different types of noises will be used. So it depends on different systems. So I'm not familiar with this vehicle, uh, but for the cell, if I want to say like, people go with like Gaussian noise. Okay. So like I'll just cover that part in the next like in the tomorrow. Okay. And then on the Gaussian noise, and then like random noises. So again, the selection of values always like depends on uh, some people follow like trial error method. Okay. Yeah. Or like modeling of some modeling approaches are there. So that big depends on like dynamics of your system. Yes. So that is how you are going to define your like noises to the system. Next, like I'll talk about something on the Kalman filter family. So before that, like if you have any questions in terms of understanding the process, you can just let me know. I will just try to explain once again. Okay. Yeah. Like how the flow takes place. If you have still any confusion, just let me know in the chat box. Yeah. So I think I will go to the next part. So when I talk about like Kalman filter family, so I'm just going to give some basic information. I'm not going to teach or not going to like go into the deep into the different Kalman filters. So once some topics like where we can touch that what kind of Kalman filter we can go for on one particular application. Yeah. So the Kalman filter, like it has like some linear Kalman filter, extended Kalman filter, unscanted, ensemble Kalman filter. So again, in their respective, they have like different like DEKF. So DEKF is nothing but dual Kalman filter, square root Kalman filter, and there are a lot, etc. And extended Kalman filter, iterated extended Kalman filter, dual EKF. EKF is nothing but extended Kalman filter. Okay. And AEKF, that is adaptive extended Kalman filter, and etc. So again, in the section of like unscanted, sigmoid point Kalman filter central difference. So almost like they have the same characteristics. So they have some the similar, the same names itself. And AEKF, that is adaptive EKF, etc. So all Kalman filters follows the same what you say this all having the same steps, that is predict, like most, and update, okay, and the measurement. Yeah. So the difference is that like if I want to, I'll just take one example to define like how they are different to each other. So the linear Kalman filter application, when we go for when the system we develop is a linear, okay. So it has a linear changing behavior. So based on that, we are going to apply your linear Kalman filter. When the system is like non-linear, we can make use of extended Kalman filter and the unscanted Kalman filter. Okay. So apart from this, we have like seen different like EKF, that is adaptive EKF. Okay. So I'll just give an example like why these kind of different variations in terms of Kalman filters. So if I am using extended Kalman filter for my application EKF, okay. So whatever the noises I'm giving over here, okay. So these will be constant. These will be constant, okay. So if I go for EKF, and these will become dynamic. So these also like keep on updating themselves. So yeah, some kind of two more like equations are going to be added. So we call that as like innovation steps and um, residual steps we are going to bring in the states, and accordingly we update, okay. And then there is a different methods of linearizing your states, like the whole system, like some follow like tailored series, Jacobian. So the different methods, they are defined with a different Kalman filter names, okay. So for example, like as we see in the assemble Kalman filter, so they are using some Monte Carlo approach, okay. And then there is something called like Kubecha Kalman filter. There they are using like some D Cholesky approach for linearizing the system. So yeah, so within that the steps will be same, that is predict, update. So again within that like linearizing the system, okay. updating your like noises. So again, like there are different methods. So if you have followed the different methods of updating them, so you're named with a different Kalman filter. Okay, so most of the remain same. Yeah. So if I take like dual EKF, or like when you have like lot of data, uh, or like lot of characteristics for a system, and both has to be like continuously updating. So you will be like running two Kalman filters. Okay, for the parameters and for the states, something like that. Yeah. So like how to select the best Kalman filter. So like as we are the main topic on the battery. Okay. So we'll like discuss on this part, that is the Kalman filter for your battery application. So one with a linear model. Okay, let's say like if your battery is of linear, uh, so you can go with a simple Kalman filter, that is KF. And if the battery is like characteristics of non-linear, so if you take a lithium technology cell, okay, so it is a like a non-linear system. So then you can have to use for like uh, EKF or the UKF. Okay, and about the PRAS and the data assimilation and the further computational requirements. So if you have like if I want to talk about like computational requirements, like your UKF requires a lot of computational requirements. Okay, so for your battery, uh, and EKF compared to the UKF, like it takes like less computational requirements. Like presently, I don't have that particular data yet. Okay, so based on that, they are going to select like which one has to be, and also like on the model complexity. Okay, like you have to choose like what kind of Kalman filter. Yeah, on the data assimilation, like it doesn't mean like it means that that as I was mentioning about uh, dual UKF, right? So when you have a lot of features input for your battery, like for your battery system, like from the battery system, then you have to use like dual UKF, sorry, dual Kalman filter, dual EKF. Okay, so one for the parameter estimations and one for the state estimations. So something like con consideration has to be done when you want to select the uh, best Kalman filter for your battery state estimation. Okay, yes. So this is something you can call it as like advanced. So not to worry about right now. So so just like let us know that if you have understood on the Kalman algorithm approach, just understand the mathematics. So on the tomorrow session, like once we have jump into the cell represent in state space and the like prediction of your temperatures, SOC. So yeah, you have to be like understood it carefully. Let's say like if I take, so all these equations you're going to see, we are going to represent in states. Yeah. So tomorrow we can discuss all these equations as it is a day 2. Yeah. Till now, like if you have any doubts in terms of understanding the flow of Kalman filter, just let me know. So based on that, we can discuss. Okay. Yeah. So I plan today on covering some introduction on the Kalman filter and steps involved in it, and some approach of the algorithm, how it flows. Okay. So, and some basics on just a throw on the Kalman filter family and the selection part of it. Yep. So in the next session, like that is on the tomorrow, we'll completely go into the uh, cell model representation in the state pairs with the help of Kalman filters, and like cell thermal model. Okay, yeah, and also a MATLAB demonstration, the results discussion.